participation is much appreciated.
Welcome to session 1, titled Unlocking the Potential of Critical Metals for Atmanirbhar Bharat. This session promises a series of enlightening talks from leading experts on the strategic importance of critical minerals for India's journey towards self-reliance.
To preside over this session, we have the honor of welcoming our session chair, Dr. D.K. Singh. Dr. Dhruv Kumar Singh is a visiting professor at Aarti Dhanbad and former head of hydrometallurgy and rare earth development section at Bhabha Atomic Research Center, as well as a professor at Homi Bhabha National Institute, Mumbai. A gold medalist in MSc Chemistry from Magad University, he earned his PhD from Mumbai University and conducted postdoc research at Florida State University, USA. With over 3 decades at Bard,
we also have the honor of inviting our co-chair, Professor Shatrughan Soren. Shatrughan Soren, sir, is an associate professor and head of the Department of Fuel and Minerals and Engineering. His research focuses on sintering and pelletization of iron ore, iron making, and steel making.
we now cordially invite Dr. Singh and Dr. Soren to kindly come onto the dais and conduct this session.
We request Professor Shravan Kumar, sir, to kindly come on stage and felicitate our chair and co-chair.
Thank you.
Please give them a big round of applause. Thank you so much, sir.
So the first technical session of inauguration, the theme of the session is unlocking the potential of critical minerals for Atmanirbhar Bharat. And we are very fortunate to have eminent and distinguished scientists and personality present in this for these particular sessions. So actually one Dr. Ramanuj Narayan, Director IMT has not come, he will come today evening, so we have shifted this talk to tomorrow session. But we have Dr. Dipendra Singh, former CMD, IREL India Limited, and Dr. Raghavan Tiwari, Director of Materials Group, BARC. And then Sri Sarma Bhavanji, Deputy Advisor Niti Aayog. So all these 3 talks and all this from the very distinguished personality in the subject domain. So it will be very technical enriching, and then knowledge and information also you will get from all these things. So without wasting much time, I will just introduce the first speaker, Dr. Dipendra Singh sir. Formerly served as the Chairman and Managing Director of IREL India Limited under the Department of Atomic Energy. With over 3 decades of experience, his expertise encompasses strategic corporate planning, research and development, project production management, and quality systems. Holding an MTech and an MBA, he successfully applied advanced research to heavy minerals value addition, driving technological innovations and sustainable practices. He has also held prominent leadership roles, including President of the Earth Association of India and Chairman of Indian Institute of Metals, and Council committees. These are the very important committees as far as the national policies are concerned for these critical minerals. So with this introduction, I invite Dr. Dipendra Singh to deliver his lecture.
Namaskar. Honorable Member, Niti Aayog, Dr. V.K. Saraswat, invited speakers, professors, senior faculty, students. I think I saw some media person also here, ladies and gentlemen. So it is my proud privilege to be here presenting about the critical minerals, and since we are representing one of the critical minerals, that is rare earths, and having the industrial experience. So I thought this evolution of critical mineral era in India, the RE experience, sharing the experience with you will be the apt topic. So I'll be starting from the point where our Honorable Chief Guest has stated that the critical minerals were considered the requirement or necessity of the country because we have to become Viksit Bharat by 2047. So when we have to become Viksit Bharat, definitely our human development index has to be improved. We have to come among first at least 10 to 15 countries, and that means the quality of life also need to be improved. And when quality of life has to be improved, then our energy needs will increase, and this energy needs need not to be the conventional, rather it has to be the clean energy, and the clean energy comes from the transition material. So that is one of the requirement where this necessity or inevitability of critical minerals and materials have been felt in our country. But the real evolution took place at the World Forum by declaration of Kyoto Protocol in 1997, when the developed countries were imposed capping on their emission, and these cappings were 6%, 7%, etc. And later, of course, in 2015, 2014, this was also imposed on countries like developing countries like India. So with this, my presentation is evolution of critical mineral era, the RE experience, which I would be sharing because some of the materials which are in the list of critical mineral are already mined, processed, refined at industrial scale in our country. So how the emergence of criticality is felt. So supply shortfalls, sometimes it may be natural, sometimes it may be a created one. The best example we can see very recently on 4th April 2025, China has imposed embargo on supply of rare earth based permanent magnet, especially the NdFeB magnet, and then the means inclination of the rest of the world to move towards the electric vehicles have felt or have experienced great impediment, and therefore that impediment was also felt in India, and then we started feeling the need and the initiative which was taken towards the critical mineral. So since then we have been trying to achieve this by various means, but still it has not been achieved, and just 3 days back China has imposed another embargo on additional materials other than the magnetic material, and then they have also come forward with a strategy or design that whoever are using these materials, they have to take or give the license for towards the end user agreement. It means not only the material they are supplying to that extent, but beyond that, where it is used, up to that, they have the means empowerment to inspect, to check, or when they don't find it in alignment of their policy, they can stop those processes. So this is a created supply shortfall. Then with that, the demand spikes, but can we predict it any time? So it is very difficult to predict that when it will happen. So therefore, we have to be ready well in advance, and we should not wait the crisis to come to our doorstep. And we have to be ready to find the solution that how are we going to respond when such situation is happening or knocking our doorstep. So this is the bar diagram showing mineral demand for clean energy technologies by scenarios. There are 2 scenarios. One is sustainable development, which is the requirement as per the policy, and then there is target of net zero by 2050. And what are the sectors? The hydrogen sector, electricity network, EVs and battery storage, other low carbon power generation, wind, solar PV. So we can see that with the help of this bar diagram, there is a steep rise in the for the requirement of these minerals. And who is representing the highest rise is that EVs and battery storage. Again, it leads to the requirement of critical minerals and materials. Now, growth of selected mineral in sustainable development scenario by 2040 in comparison to 2020. These are the data of Department of Energy. So lithium is likely to increase as per the sustainable development policy by 42 times, graphite by 25 times, estimated cobalt by 21 times, nickel 19 and rare earths 7 times. I think something similar figure were shown in a different way by Honorable Member. Now, changing fortune, today coal is a major source of energy, and coal has been declared in 1974 because of the coal energy crisis as a strategic sector, and from there onwards we have seen considerable rise in production and supply of coal. So what is the scenario in 2020 and 2030 and 2040? If we look at the fortunes are changing, the today's coal fortune will be changing to the energy transition material. And what are these materials? These are listed in the rightmost corner. And here, of course, the highest bar is of copper. That is also in the list of critical material of India. And the other materials are also occupying their own slots. Now, for energy transition, what is the requirement of mines? This is the global figures. So the biggest requirement is coming of copper. So copper has average mine size is considered 60,000 ton. Available capacity is 22.9 million ton, and additional 3.7 million tons have to be created. Similarly, the other materials like graphite, nickel, lithium, synthetic graphite, manganese, cobalt and rare earths, the existing capacity and what is the additional capacity is required to achieve that sustainable development objectives. These are the figures which are the estimated by again Department of Energy. Now this is the slide showing what is the Europe's dependence on Chinese resources for various critical materials. So heavy rare earths, 100% depending on China. Here there is slight misinformation in the market. Normally it is said that rare earths fully dependent on China. Even Indian dependence is considered on China. But it is not the truth, because the other lighter rare earths like NdPr are supplied by other countries. India is also having a small share into that. But as far as heavy rare earths are concerned, this is totally focused to China. No other mines are producing these materials. In Indian resources, it is available to the extent of 1 ppm dysprosium and 0.5 ppm terbium. 1 ppm in India, REL has established a small plant extracting it with the support of BARC. This plant was established, and I think Dr. D.K. Singh worked on that. And now we are supplying it back to BARC. So the total production is very less because the content is very less. But heavy rare earths, as far as industry scale is concerned, the total dependence is on China. The magnesium, 97% dependence, light rare earths 85%, lithium 79%, and then you can see the other materials that there is a lot of dependence of Europe on China. Now here we have to also look into one important point. When we say that this dependence is there is an ecosystem of supply of these materials, of the refinement, not in terms of the mineral or material, rather refinement in terms of the product, value-added product. So normally this route goes from China, Japan to Europe and then to US in the defense. So when Europe dependence is there, it can be said as a global dependence. Now this is the difference. See, many a time we hear that we have to increase the mining, we have to open more mining. Of course, that is also required. But at the same time, I think yesterday also Honorable Member highlighted that, today also he was highlighting that what is required, that we have to focus on processing and refining technology. And when now these critical minerals are open to the private sectors, then this need is badly felt among the industry fraternity, because they are ready to take mine, they are ready to invest, they are ready to put money into that. But when the question of technology comes, they find it very difficult, because most of these technologies are guarded. They have roamed around elsewhere, but difficult to get it. So mostly there is a dependence on homegrown technology. So how China has made the difference? This is the slide which is showing the very specific thing. You can see the cobalt. Congo is the biggest producer, or occurrence of cobalt is highest in Congo, but the refined cobalt is coming from China, so because they have developed the full capacity. Same is the case of lithium. You can find that there is only hardly 12% lithium mines in China, but refined lithium metal comes from China only. So they have developed expertise in processing and refining, and that is the key today. This is another important thing. We see critical minerals from a same lens, that they are critical for our country or for the requirement. But when we look at them, how they are divided, they have divided in two categories: advantage material and shortage material. So advantage materials are those which gives a strategic touch, or which are meant for niche technology. Like you can see vanadium. Vanadium is used for alloying titanium, which is going into the engine of aircraft and important components of aircraft, fighter jet, etc. Rare earths also falls under this category, because rare earths itself cannot give any product, but its addition into another product can increase the value of end product multifold. So this example we see with Toyota, that IRL and Toyota has a agreement of supply of rare earth concentrate, and both of us has a refining and processing plant. So they are taking from us at very high price. Their plants do not generate profit, but when it is going into the Toyota Prius or Toyota Lexus, all the profits are coming from there. So this is the case with almost all critical materials. Of course, it is more in case of rare earths. Other critical minerals, it might be lesser, but the ecosystems are longer, and therefore one has to wait longer for getting their return on investment. And there are other shortage minerals, like there is copper, aluminium. So these shortage mineral, getting technology may not be difficult, because when this is a shortage mineral, everyone wanted to contribute, everyone wanted to use. So these technologies will not be guarded, but their technology would be guarded. So we have to focus more on them in developing the technologies. Now this is the example of what critical minerals are used in F-35, and this is the main reason what we see always in newspapers and media, that trade war between China and US. So basically, it is US which has facilitated the development of such facilities in China, but today they are standing across, and every time for supply of some of these materials, China enter into the trade related war or embargo, etc. Now, there it is the material, but here what are the components and what are the alloys used in this combat aircraft. So along with the alloy used in a component, and what is the technical specification prescribed by the aviation industry, those details are given in this slide. It is because of the time shortage, I am not going into detail of it. Now this is another important slide, that how rare earths power defense sector. So F-35, there is 418 kg of rare earths used. The different materials which are used are given at the bottom. In destroyer, Top 51 destroyer, 2,600 kg of rare earths is used. And again, you will find something similar material, what was used there. Most of them are rare earths. Then in submarine, 4,600 kgs are used, and again the same set of material which are magnetic, luminous as well as laser specific materials. So this is the importance of rare earth for the defense sector, and this is the whole thing which is reflecting in the newspapers, media, in terms of expressing criticality of the rare earths. This is related with the carbon dioxide emission. So, an example of rare earth permanent magnet motor based on NdFeB magnet is taken. So, the longer bar in the left side is for the induction motor, which is showing the weight difference between a REPM based motor and induction motor. And same is the case of here, that what is the CO2 in terms of kilogram equal is emitted in this production process. So the red portion is showing how much carbon dioxide emission is there when the rare earths are produced, processed and refined to make the motor, and rest of the things are other metals. So here the difference is that even for other material, the carbon dioxide emission is reducing with the application of rare earths. This is our day-to-day usable items, laptop, so you can see what you are using, how many critical material and rare earths are there. In smartphones, every layer you will find there is usage of rare earths or the critical material. And another important aspect, see, when we work on anything in the Department of Atomic Energy, we were always constant with the material of construction. And because of this constant, when we go for engineering of any of the concept development into realization of the product, then sometimes the material of the furnace is creeping into the product, and so on and so forth. So material of construction is very important, and these are few of the examples how the alloy has to be built in and which can find application, niche application in various sectors. Now coming back to the Indian context, now these are some of the critical material which are already produced at industry scale in India, and this is the experience I'm going to share in my talk here. So this is the under Viksit Bharat, what are our targets, how many times like third largest economy, and increased share of new energy vehicles. This has been explained in detail in the inaugural lecture. This is also explained in the inaugural lecture. So now I'm coming to the extraction process. In general, with our rare earth experience, we can say that these are the processes, whether it is a placer deposit based or it is a rock deposit based. So the mining portion, ore is coming from the mining, that there is crushing, grinding and classification of liberated ore versus what is the subgrade material or what is the waste material. Then there are physical beneficiation where, because most of these materials are occurring in a very small percentage. If you look at the current auction process, most of the cases you will find that cutoff is 0.1 or 0.25 or 0.40 percentage. So that means if you have to understand the enormity of the subject, that means that from 99.6% or 99.9% waste you have to handle in physical beneficiation. And these are the processes like gravity concentration, magnetic concentration, flotation, electrostatic separation. All of them are used in IRL plants, which I was working earlier. And then comes the acid or alkali leaching, precipitation, solvent extraction. So here the beneficiated ore is exposed to these processes, but here again, what is the beneficiation level we can achieve? It depends on that. If we don't do high level of beneficiation, then at this stage, again, a lot of impure compounds will be generated and disposal will be an issue there. And maybe if we don't address it aptly or properly, then getting clearances for the industry scale process becomes difficult. And of course, the refining is through solvent extraction that we will see later. So this is the overall process, mineral production. When we look at the resources, so China is the major producer. Now here it shows only one aspect of Chinese resources, that is a bastnasite based, and there the rare earth grade is 6%. But they also have the same resource what India is doing. But till today, no one is knowing what is the capacity of that and from where they are arranging the feedstock for it. So that's totally hidden, nowhere in public domain. So we are comparing with only what is available in public domain. So their resources are around 100 times higher than Indian resources. So that means for doing the same level of activity, we will get 100 times lesser product than them. And the required element like NdPr, samarium, dysprosium, terbium, these are the percentage and ppm level. I have explained earlier what is the dysprosium level and what is the terbium level at which REL has been working. Now, what is the impact when this grade differentiation is so high? And here I would also like to mention that beyond China, US has the resource of 89.9% and Australia has around 8%. Other than every other resources are lesser than China. So the difference is this comparison of the process. Obviously the cost will come higher when it is a lower percentage, and cost will be comparatively lower than the average grade is higher. So with this impact, I come to straightway the mining methods employed for rare earth mining. Actually, apart from this rare earth, there are 6 other minerals also apart from the rare earth minerals. So therefore, this mining is done by either manual because of the CRZ classification and regulation. Then also it is done by dredge, which can be seen here, and then by the excavator. This depends on the water table, what kind of mining we are going to adopt, and the regulations available in the mining area. So these are the mechanical mining. The importance of this mining is that at the same spot we can do the beneficiation, and if the ore content is 10%, 12% or 8%, then rest of the material is separated and put back into the mining area, and that is the basic requirement of the sustainable mining. So this is again few of the pictures of the dredge which are being deployed in our country. And now when you have a low level of resources like 0.06%, so how the beneficiation has to be done, that is explained in these slides. So in the second stage of beneficiation, from 0.06%, it is called a concentration operation or beneficiation operation. The REO percentage is increased to 0.6%, and then it goes to the next stage of beneficiation, which is called mineral beneficiation or mineral separation plant, where all the other minerals will be separated from the rare earth mineral monazite, and then the REO concentration is achieved up to the level of 25% in the third stage. So these will occupy already 3 plants, and here the other product will come into the market, and that gives the revenue by which we are able to make the process economically viable. And in the 4th stage, this is the rare earth extraction activity, which is chemical. Before that, everything was physical beneficiation. From here, it starts a chemical beneficiation, where the rare earth concentration increases up to 45%. And here, the rare earth is extracted in the form of a concentrate, which is in the mixed form of all the 17 elements in the different proportions. And then this rare earth concentrate is exposed to the solvent extraction process, which we call it as RE refining in terms of rare earth oxide. And in this, first the heavy rare earth stream will be separated, and then afterwards this light rare earth stream will be separated into lanthanum, cerium, neodymium, samarium, etc. This is the permanent magnet plant which was set up in Vezar by IRL. This is another plant which is set up in Bhopal, where 7 working plants are available of different metals of rare earths, neodymium, praseodymium, titanium, lanthanum, cerium, etc. These 2 projects have been done with the support of BARC, and today both of them are operational. And heavy rare earths also, this gadolinium and dysprosium we could extract from a very low concentration. These plants are also operational today. This RE sustainability program, I think that there is a separate lecture, so I am not going into it. Now, what are the strategic initiatives needed for India short, medium and long term? So, strategic exploration, resource mapping, incentive-driven private engagement. I think this area government has already done, again with the active support of Niti Aayog. Supply chain development, I think we have to see it instead of value chain from the perspective of supply chain, because this is need-based, this can happen faster. Dedicated processing hubs have to be created, then skill development is another important aspect, advanced manufacturing, and the most important aspect is the regulatory support, because by our experience we have found that this is the area which is most ignorant in our country. So these risks in the first lecture have already been explained. Now what are the technical barriers? Most of the cases are lean grade, so therefore volume of waste generation is very high. Polymetallic nature, therefore though revenues will be smaller but plant size would be bigger, the spread will be very high. Sometimes it is misunderstood also. Flow sheet development, in our country, yet this skill has to establish, the engineering aspect has to be established. Even the testing facilities are not available to full scale. Then purity levels, we may have to sometimes compromise because of non-availability of all this. Then what is the structure of market? Like in India, we don't have a perfect market structure for this material, which is the prime driving force for that. Waste disposal is an issue. Customization, yet we have to develop our orientation towards that. Consumption is low, so therefore this consumption also have to be increased, and therefore the revenue is low. And finally, the dependency is very high. Like even if today we start manufacturing some of the important items, the component ingredients are yet imported. So the dependency continued. So in one of the meeting when this was discussed, that what is the value addition percentage in different aspects. So this is, I am talking about 2 years back. So highest value addition in such type of product was found only 11%. So this is our challenge. So with this, Jai Hind.
Thank you very much, sir. Actually, this needs more time, but due to shortage of time, but I think we will not have take any questions, because the time is also honorable member wants to visit some other facility. So actually we don't have to, we will take the questions during the lunch time. And
you should allow 1 or 2 questions.
1 or 2 questions. Okay, sir. One or two quick questions. If anybody would like to ask them. So, yes.
Sir, thank you for a very nice lecture. Yeah, thank you. So I have a very preliminary kind of question. How much cerium India is producing? Because you have mentioned somewhere the extraction has already been established at Bhopal.
See, the Indian capacity to produce cerium is 2000 ton TRU and about 1600 tons of TRE. And if you look at from the concentration viewpoint, it is around 10,000 ton. Because in rare earths, there are number of terms. When we go into the market, if we just say rare earths, I think we will not get any response. So we have to explain it in terms of TREO, TRE, concentrate, and so on and so forth. So that is the established capacity, 2,000 ton. Out of them, 50% is Indian capacity, 15% is the Japanese subsidiary. This production depends on how much NdPr is required. Like in India, NdPr requirement is very low today. So IREL do not produce all 983 tons of cerium. IREL is producing only 25% of that because there would be a storage problem. So that adds to the cost. And cerium is not having any criticality. Rather, when Chinese issue the invoice, they give cerium as add-on. Add-on means no cost.
Thank you. So please give a big round of applause. Very excellent question.
Thank you so much, sir, for that wonderful talk. We now request the session chair, Dr. D.K. Singh, to felicitate the speaker with a memento.
Distinguished scientist, internationally known metallurgist. And again, I will tell that we are fortunate, particularly due to time constraint, we are not able to give them much time, and looks very odd to. So, next topic is on the materials for the generation 4 nuclear reactors in India. So before I call Dr. Raghav Tiwari, Director Materials Group, Bhavat Credit Center, I just would like to read his brief biodata. Dr. Raghav Tiwari is a distinguished scientist, Director of Materials Group, Bhava Research Center, and Senior Professor at Dhanbad National Institute, Mumbai. He has specialized in physical metallurgy, refractory metal alloys and materials for nuclear reactors. His key contributions include leading the development of destructive material for Generation 4 reactors and pioneering India's first indigenous scanning electron microscope. He currently serves as the President of Electron Microscope Society of India, a prolific author. He has published approximately 400 papers and 4 patents and received the G.D. Birla Gold Medal Award and Fellowship of the Indian Academy of Engineers 2024. Actually, many more awards are there, but due to time, I am not
Thank you.
Please.
More than sufficient. Okay, I am Raghav Tiwari from Materials Group DRC. Actually, I wanted to give lecture more on the rare earths future application and all, but Dr. Singh told me that you should look on a different perspective because everybody is going to talk one aspect of this other. You talk on the materials for Generation 4 reactors. So I have taken this liberty. Some of you may find this is slightly off the topic, but I request you to bear with me. Okay, so let me start. And at the outset, first of all, I want to thank Dr. D.K. Singh and Dr. Mishaji and other colleagues, Dr. Professor Sharan and Dr. Professor Deepti and all for inviting me first place, and very nice hospitality. Thank you very much for that. And see, point is, country currently growing at a rate of between 7 to 8% of GDP. Now, this much of GDP production requires a lot of energy, and this lot of energy comes by the import coming from in the terms of the hydrocarbons from foreign country. Now, this is not coming cheap. It's a very costly proposition because nearly 5% of our GDP is drained in securing this. Rather, you know that today's entire geopolitical or foreign affair is just like a pivot point is the securing the energy requirement. The first time the calculation around 2015 or 16 was done when people figured out that if India is allowed to grow with this rate, and that is energy being sustained by the hydrocarbons, by 2035, very, very conservative estimate, that 10% of the world demand will be coming from India. That means 10 liter petrol, 1 liter should be Indian. Now that time the Western world first time got sort of worried about or concerned about. So what they did, they came out with the idea called the carbon footprint. So India was asked to sign a treaty where they have said that by 2070 they will cut down the carbon footprint to zero. Now, saying that bringing the carbon footprint to zero is one thing, but implementing is another. Now, when they try to implement, they look for the solar energy, they look for the wind energy, they look for the hydro, they look for the sea wave energy, all put together, they could not put a small dent in the energy requirement. Then they decided to go as an alternative energy about the nuclear energy of that. Now, nuclear energy before that was considered more as a taboo. So our nuclear program was given just money to survive so that technology can be kept alive. But beyond that, they were not looking forward for this kind of things. After 2016, suddenly a jolt was given, and we were suddenly, the department which was producing 7 gigawatt is asked to produce 100 gigawatt by 2047. Now this is changing the game altogether, and that is why I had to give you a little bit sort of pretext or context so that you understand, is that India was not a suitable country to go for the nuclear energy at the first place. Reason is that uranium we don't have. Means now we have discovered some places, but they are very, very lean ore. Very, very difficult to extract uranium from them. Rather, in the best form we have very near to you is in the Jadugoda. So what is happening that Baba was a young person, over enthusiastic person. He said, we will make uranium. We will make the nuclear energy. If nature given fuel, that is uranium-235, one isotope of uranium, if uranium is less available, we will make other elements as the fuel. And that is why a very complicated journey started. That is, I think here, if you see in the bottom line, they are called fertile elements, which can be converted into fuel, that is fission. So he selected thorium and uranium-238, which will convert finally into plutonium-239 because of the neutron absorption, or thorium, which will convert into uranium-233. Fortunately, we have one of the largest resources of thorium in the Kerala to all the way up to Orissa, the availability of thorium, so this can be used. So that's why Indian nuclear program is a more complex program. Unlike the program where the top one shown over there is that where Americans, they take the fuel, put in the reactor, fuel is over, they just go and deposit it. In Indian system, we don't do that. we put the fuel, use inside the reactor, allow some of the uranium-238 to convert into the plutonium-239, then reprocess it, and again take it back to the reactor. So it's a very complicated design started, and this is what we reflected in 3-stage neutron program. Some of you may be aware of, some of young person may not aware of that. The idea is to extract as much as energy from thorium. If you just do the back of envelope calculation, you will find if we can harness this or we can master this technology, for 5,000 years, we need not to worry about the energy production, electricity production particularly. So this much potential is there, so we wanted to go on for that. The idea is you use natural uranium with the limited resources, convert the U-238 element, which is another isotope of uranium, to plutonium-239, extract it and give it to the fast breeder reactor. And in fast breeder reactor means my neutron energy is 1 MeV. So what happens that plutonium burns best in that. It will produce so many neutrons that now you start taking thorium into that and converting into the uranium-233. So stage 1, natural uranium, stage 2, plutonium, stage 3 is the thorium. The idea is once the stage 3 comes in, the stage 2 and stage 3 have two qualities. One, that they produce their own fuel over time. And that's why the terminology was given was Akshay Patra, that you take the material out and new material is produced. So they become self-sustainable system. So after we master the technology of third stage, first stage can be dismantled. But it looks very good on the paper, but when you start working out, the problem starts. And now after nearly this, Baba gave this idea of roadmap in 1960s, 60 to 65, 65 he got. So in those 58 to 62 he was developing this concept, and the PHWR concept started in 70s. But we mastered the technology by the time we reached 2010, 2012. It took so many years because of the critical requirement of several technologies and materials which were not existing in India. See, that is why ISRO has one very good advantage. They make a small satellite. But if you do not know that all the screw come from Japan, so your satellite is half Japanese. But in reactor we cannot do that, because the moment you do that, by international treaty, these people will come and you have to provide all data to them. After, when we had a lot of terrible problems with the uranium availability, we have undergone that half of our reactors are now sort of exposed to the international audience. So whatever material movement we do, we have to report them first and do that. That is one other issue which need to be addressed. But we are the largest custodian of the first generation, that is PHWR kind of reaction, pressurized heavy water reactor. The second fast breeder reactor is one of the unique in the world. Last week I was in IGCAR, they were lowering the fuel now. So by January 26, it will go to critical, expected to go critical, and by 27 January, we will attach it with the grid. That is the first time in the world that electricity generated by the fast breeder reactor will be fed to the feeder. Generally, fast breeder reactors are there, they are used for other experiments, not for electricity generation. So once these two technologies are done, then we think of third technology, and I will come back to that why. So we have, if you look, we have currently 25 operating reactors, in between one is added. So 25 operating reactors, this is the largest battery of PHWR on the world. And if you look, we have the world record in continuously running the plant. That is 962 days, 3 years has gone, and is still continuing. So this kind of the reliability we generated, condition is your electricity cost should be less than 5 to 10 rupees. It should be in this range per unit. For example, EPR, European reactors, they give you electricity at the cost of 40 rupees per unit. Who is going to buy it? So there are technology available, but idea is to bring the money as low as possible. Now, with the current 100 gigawatt electric production by 2047, we have to just jerk up the entire system and come out of the loop of the what Dr. Baba proposed. So you can see the red marks are given for all those future coming reactors. And if you calculate, they are nearly 3 times of the current reactor. So from 7, we will go close to 40 gigawatt by this process. Now we had to reach 100. So the gap was generally filled by what we call now as BSR, Bharat Small Reactors. These small reactors will be double contained so that radioactivity, what may come, should not spread beyond half a kilometer. So all aging NTPC plant will be replaced by those. And then we have few more ideas which are coming from this picture, very famous picture, you probably may not know that. This is Fukushima. In Japan, nuclear accident took place. See, this was not a nuclear accident for the first time. The unprecedented 9.2 Richter scale earthquake shook the foundation of all these reactors. But very heartening thing was reactors shut down very coolly, the way they were designed. But followed by the tsunami, which again was unprecedented. For 1 lakh, at least till human race existing on that island, nobody has seen such kind of tsunami. It came and it started filling the reactor. See, if you want to shut down a reactor, it does not just like you cannot switch on and switch off. There is a radioactive decay, so you have to extract that heat. So secondary sources, generally pumps are there which can cool it down. They got stuck because of the tsunami. And as a consequence, the temperature started increasing and zirconium and water started reacting. Hydrogen produced, excess hydrogen pressure caused the damage. If you can see on the left side, this below, the first reactor which blew off few days before, it is there. Second, you can see the smoke coming out, the steam coming out, the second one, which blew off only few hours before. And most heartening part was, not a single person till today died because of the radioactive decay. Whereas 200 people died while they were evacuated from the system. So all critical old people, all infant child put together, 200 people died. So the panic of radioactivity is more severe than the radioactive fire itself. This is the point I wanted to. Now this has gave a new concept that why to put zirconium and water in place. Let's separate them out. And that is why many concepts started coming up. The 3 which are highlighted are being pursued by IGCAR, and the 3 which were open, they are being pursued by BRC. So I will, for this example, I will just take the gas cooled fast reactor and molten salt reactor just to explain things, otherwise it will become too long a talk. Now what you can see that in all these, coolant is non-aqueous, except that supercritical water, you will have water of course, but otherwise all are the different materials, gas, molten salt, molten metal, and all those kinds of things are there. And cold temperature started going above 500, 600 degrees centigrade, so you can have higher efficiency on that. If you see, nowhere zirconium is being used. Zirconium has been completely removed from there. So I will just now take these 2 reactors. 2 concepts exist. One is called prismatic core, where you have a feed, that's a hexagon is shown, graphite hexagon. Inside the porous rods will be done. We have the fuel loaded in that, and gas will pass through and take away all the heat. They are expected to operate around 700 to 900 degrees centigrade, so that we can club them for the production of hydrogen. So by production of hydrogen, you are cutting down the carbon footprint little further. That was the basic idea. Now there are 2 designs. One is called the prismatic, another is called pebble bed. In pebble bed, you keep dropping the pebble, and it is more like you have seen the grinding machine is there. You put the grain from top and collect from the bottom. This concept was there. This looks easy, but the problem is, the better, if you want an operation, then the first one provides you better control on the neutronics, temperature and fluidity of the gas. The second is when it generates hot spots. Chinese claim that they have made this reactor, but after that they don't give any data. The reason is most of these reactors, they were operated and shut down not because of the technique, not because of any other problem. Problem is they were using helium. Helium is already so much scarce gas, and the leakage rate when they calculated, constant supply was not there. So slowly they decided to shut down the reactor. So we have taken this clue. So we started changing the design, and currently our application is to use carbon dioxide gas. Now conductivity of carbon dioxide gas is way low as compared to the helium. So you have to modify the design to suitable for that. So currently Government of India has given our 2030, the first reactor should be installed. 32 it should be operational. Now these are the time scale we are not very accustomed of. So we were given 1 decade time at least because that's the time design takes. So now we started running for the development of material. So as a plan B, one steel was to be developed. Now steel in front of carbon dioxide 700 degrees centigrade will not survive because carbon dioxide gas has a tendency to form carbon monoxide and depositing carbon. And so any steel which can take carbon should be designed. So lot of experiments were done to figure out which steel gives the best. This is the plan B, not the plan A. So what we have done, we have developed one steel. We are now going for the production of that. This can give, because fuel tube do not remain inside the reactor throughout the life. When the fuel is done, you have to pull it up, throw it back. So for a period of 2.5 years, they can sustain without much problem. Couple of testing are done, few more are required to place this material into the reactor. But the idea, these are not the plan A. This is plan B. This is that if suppose plan A does not work, then you have to restore it. Now another material is about graphite. Everybody talks graphite is a critical mineral. I was also not understanding why. Because graphite has an advantage that graphite is available everywhere. Where you have tree, you can have graphite. But the story is not so simple. Because graphite and nuclear grade graphites are two different entities. For nuclear grade graphite, you should have isotropic nature, means I take sample in two perpendicular direction randomly and check their properties. If their variation is greater than 1.1, then it is not a nuclear grade graphite. Then the density we want more than 1.8 gram per cc. Most of the graphite we available 1.6 to 1.7 gram per cc, whatever we use, take graphite from India or anywhere. So now the third problem was the boron equivalent should be less than 2 ppm. This creates a problem. So if you want to put this thing in the international market, they will immediately come to know you are looking for the nuclear graphite, they will stop the supply for you. And unfortunately, we are basically another set of people who do not have any materials. So this is where the issue comes in. So we have to make graphite our own way. So we started working on that. If you go for the graphite is another, you take from different source property, change it drastically. So we started developing these mesoparticles and started working on that. And based on that, we have developed our own flow sheet, which is shown over here. And this flow sheet, we used it to develop the materials. So now this technology is available, and in Gujarat, one company has taken from us. So we can make up to 400 meter, half meter long bricks we have made. And the properties, if you see, the density required 1.8, it is 1.85 to 1.87. Boron equivalent 2 ppm, it was no boron was there in ppm level. Whatever is there in ppb level. And isotropicity 1.05, you see two perpendicular direction, one with the black line, another with the red line, you can see the properties are well below 1.1 into that. Actually it is 1.05 at the worst condition. Okay. Then the next concept came out that this is the core material. So now let us make the carbon-based material. In India, nobody makes the carbon fiber to NPL daily makes because of the missile programs and all. But they make very small size. If I make a tube, I require 2 meter long tube. And that is where the problem started. So we started making our own carbon graphite material and try to convert into the silicon carbide. Now silicon carbide making is not an easy, silicon carbide technology does not exist in India. So what we did was that we started with the polysilicon, carbosilane, and then converting them into by successive curing and pyrolysis process into the tubes. So this is nearly half meter long tube which a cap on that. Now the point is how to join these two. So this issue was there. But when we had gone with this proposition, they said no. Graphite or carbon-based fiber will not work. So we should go for the silicon carbide materials. In silicon carbide materials, we roam around the entire country, not a single institute, not a single private company, not any academic people, they make silicon carbide fibers. Some millimeter size or 1 centimeter, 2 centimeter size are there. I didn't know the cost at the time also. So we taken this challenge, we started making the different material. This is for the carbon fiber, carbon silicon tubes we are made. These are available in the market. Now technology was transferred. Making silicon carbide fiber is the second task taken. So again, dimethyl dichlorosilane was started, polymerized. Then we used our own different rearrangement systems and gone for the fiber making. The machine on the top left is our own indigenous design, where carbon fibers are melt, spun and made. After that the pyrolysis and that is started, and in this process a very unique furnace is made, where within this furnace, this is a vertical green color vertical furnace. It has 6 temperature zones and your fiber has to pass to a particular sequence. So the spun one they were made, these spun were allowed given a different path. So if 200, it has to stay for 20 minutes, it will go through a very circuitry path to remain 20 minutes, then it go to second, where it has to retain, suppose for 10 minutes. So you have to change the path, because it should be a continuous fiber. So we have produced 500 meter carbon, silicon carbide fiber now, very well, we can regular basis made. I didn't know the cost. So we used to make it and keep it aside. One day, one person came, he said half meter of silicon carbide fiber of this quality cost more than 5 lakh rupees. And we have 6 spool of 500 meters to 1 kilometer. So immediately we found out 5 crore rupees were lying on the ground. So that was first time removed. So this is the sort of a, we were trying to do readiness. Now many of these technology are available with BRC or DA, but we find that the takers do exist, but they don't want to sustain it. Many times, see, BRC has one disadvantage, that we have science, we have technology. 2 axes we cover very nicely. The third axis, that is economics, this is where, being a government organization, we are the weakest in the link. So when the commercial part comes in, we do not able to do that part. So we started making another concept, that is silicon carbide composites. Now silicon carbide particles are made, then we bury them under the carbon powders of various sizes, because the density I have to reach 97-98% to make it nuclear applicable. All those what I have shown, they are available for open market, but they cannot go into the reactor. So in this way, then we pour inside the liquid silicon so that the reaction takes place. Now the trick is how to make sure that silicon has very uniformly percolated all the way up to the down to the other end, and how you are controlling the properties. Because remember, silicon carbide is a line compound. You may end up either with excess silicon or excess carbon. So you have to know exactly what is to be done. So now testing parameter, I am not telling some of these things. We have finally reached to 100%, 97% silicon carbide. Now this material, when the tube was made, this was successfully done. Now we are testing in our fast breeder reactor to see that, because preliminary testing, you see the last line that we have done the radiation study. It shows that up to one life cycle, it will sustain no change in the property. So now idea is, can we reuse it? So we are going to give it a treatment of nearly 10 years to 15 years to see how the property deteriorate. If property do not deteriorate, they will become integral part of the reactor. Now, the second point is you have made the tube has to be sealed. So now lot of efforts have gone in sealing. That is, you provide the proper weld, because this radioactive material should not come out. So for that, we have put lot of efforts, and finally, one glass material was developed which can very coherently weld the silicon carbide. It has same thermal expansion, because temperature has to go to 900 and come to room temperature. So your coefficient of thermal expansion should match with that. Otherwise, it will break up. So with this, we have developed, most of these technology are not available, and if some companies are ready, we are ready to even share them. This technology has already gone up. What has happened that Baba Bullet, probably Baba jacket, you must have heard all of them. If not, that the bulletproof jacket now we are made with the carbon, with the boron carbides. But boron carbide is a costly material. So we use the same concept, that we taken the boron carbide particles, bind with the excess carbon and allow the silicon to diffuse. So now we have a composite. That is, we have boron carbide and silicon composite, and this can take the heavy machine gun bullet also. And weight is only 9 kg. Some 1 kg weight gain is there, but it can save the Jawan from his life. So this material, basically we are not asking for the cost. We are giving to the bulletproof jacket making company almost free of cost, so that they can quickly implement. Otherwise there is a lot of bureaucratic process and everybody gets stuck to that. Now I will come to the second reactor, and how much time I have? Just 5 minutes, give me 5 minutes, I will finish it up. Okay, so very quickly, in the molten salt reactor, basically idea is that thorium we want to use very fast. Thorium has one issue. When it absorbs one neutron, it becomes protactinium-233. And then by beta decay, it becomes the uranium-233. But if you allow it to stay inside the reactor, it will become protactinium-234, and then it will convert into uranium-234, it becomes useless, because 234 is not the fuel for the reactors. That is one. Second, uranium-234, if undergoes alpha decay, it converts into thallium, into bismuth, and generates so much of gamma that you cannot handle it. This is the one reason we are not still able to make progress to the third stage of the Baba program. So one idea is that don't allow this material, that is protactinium, for 25 days required for conversion. Before that you extract. So solid material movement is difficult, but in the liquid state it is easy. So that's why they did it, and we are going for this reactor. Now point is, the fuel is the fluoride, and fluoride fuels are difficult to handle. That's why you have to make the material. The problem is no material on world exists which can do it. So this research we have to do our own. So we started developing material for this as well, and started testing simultaneously, so that nearly 100 materials are being scanned, and then finally we optimize the composition with respect to the alloy, and we have found many applications. Now time is short, I don't want to bore you with that, and I want to go this. We have developed material and came out with a lot of problems, what are the phases, every details were there. Then we came out with a material where we find that all the properties were matching, and we came to this material was given to Midhani, and Midhani has successfully made it, and this NFC also did the extrusion process, and as a consequence all final materials are ready. Next year we are going to make the loop out of it and then use it. The point I wanted to tell you, if you look on the top is the design requirement. That is strength 690, MPa, elongation 40 MPa. Our material what we produce is 100 MPa, it gives 690, I am giving 790 properties. You asking 280, I am giving 300 property. You asking 40% ductility, I am giving 67% acidity. So this material is now ready. The first loop will come and all forms are ready for the fabrication. So because we are now waiting for the building to erect so that this loop can go and we start working the first reactor. So this kind of work was done. I wanted to show a little bit about the fusion. If you give 1 minute, or should I close it down? Okay, the fusion is basically the energy which entire universe is running on. So this is the energy we should harness. Idea is that in fusion generation, what we do is we have deuterium and tritium. Fuse them, it will become helium and one neutron comes out. This atomic energy gives the 4 times of the energy given by the fission. So in this, the only problem is that tritium elements are not so many in nature. So whenever you want to run fusion, you have to generate tritium. So that is why lithium has to be produced. Lithium absorbs neutron and converts into tritium and helium, which you can run on that. So our system was working on that. The point I wanted to draw your attention is how much material requirement. Only 400 gram of tritium, 270 gram of your deuterium for 1 day, and the laptop battery all you carry give you energy of the whole life. This is the power of this reactor system. So we started this proposition was given in the France. 8 countries are participating. India is one of them, and we have fulfilled all our requirements. Rather, France people now wanted more and more Indian to come there to join us, and this entire process has been done, process to that, and now we are going to play a major role in some of the loops, which I just want to skip some of the part. I just wanted to tell you that what is happening is that we have made this very special material where lead lithium will be going, which act as a coolant as well as act as a tritium producer. And this 1 meter, 1.5 meter TBM machine was given, tested and qualified. So now this material is waiting for the test and going ahead, and we did everything. This special steel was developed. 6 countries were in race. European, CLAM, this is China, JLF Japan, and Indian RFM. Out of them, Indian RFM performance till today is the best. So those who think we cannot do, we can do best and outperform many of the developed countries. The only required is some guts to push the things around. And then this entire loop has been made. This is the replica of that, and this kind of the complex experimental design were made to qualify the material. Had I had more time, I would have gone for it, but thank you very much for your kind attention.
Thank you very much, sir. Very informative session, right from history, science and technology, including composite material, super alloy and so many things. So, Sarasa sir बोल के गए थे, we will take quickly 2-3 questions. Okay, 1 or 2 questions.
One question.
Oh, yes sir.
Dr. Tiwari sir, wonderful talk by you. I just want to add, no question. BRC and all these things, you are strategic organizations. Henceforth, the economy doesn't come under your purview, sir. You need not to worry about those factors. I am very sure Government of India is very keen. All those developments should go ahead. Thank you, sir.
Now I request session chair to present some moment to Tiwari sir. Big round of applause for it. presentation. Now we'll technocrat. Now we'll next presentation is from policymaker. So our next speaker is Sri Sarvanavan. Sir is a duty advisor in Niti Aayog since 2012. He has take up the role after 17 years.
Sir. Aarti.
Okay, sir.
DK Singh, ladies and gentlemen, it's a difficult situation I am standing in because I am the last speaker before lunch. Apologies for that, and we had 3 wonderful sessions, speakers. One Dr. Saraswat, next D Singh, and then Mr. Tiwari sir. So after three wonderful lectures, I don't want to go into the nitty-gritties. I just want to show the position where we stand in respect of critical minerals. So my talk is exclusively on National Critical Mineral Mission, which has been floated recently by the Government of India. But before that, so I will just dwell upon what critical minerals are there. It is as simple as it is. See, actually a patient suffers from cold and cough. So there is no one to take care of that person. So after 1 month he gets critical, he gets pneumonia, all those things, and finally you put him in critical ward. That's the thing where we stand right now. Because this is our 78th year of independence, and as on date we have not done anything, any good justification for the mineral sector. I think Indian School of Mines should note it and then come with some good prescription, because all these years what we are dwelling upon? We are dwelling upon only with iron ore, limestone, all those things. Even in the 78th year of independence, we had only one very good British gold mine, Colombo Fields namely. That was also shut up by us, telling that the threshold will not work out. Because all these are political games. It is not any technical involvement, it is all political game. I don't want to go into that nitty-gritties. And then we started one gold mine, which is currently operating in Raichur, Hatti Gold Mines, where we produce 1.5 tons. But thanks to our ladies who aspire for 800 tons per year, where we are producing only 1.5 tons. You can see the graph actually, where we stand in respect of gold. So if you take next mineral as zinc, I am talking about all common minerals, I am not going into any critical minerals. You take upon zinc, where we are in zinc, only one particular entity, government entity was there, which was converted into now Hindustan Zinc Limited. They are operating 7 mines now. I think after 2030, when this particular legislation comes to a grinding halt, where the miners will face a difficult situation, especially captive miners, then that will also be a question mark. So next, take copper. So copper, actually, we produce copper. Actually, we are once upon a copper exporting nation. Some 5 years before the sterling came into picture. Now we are a copper importing nation. Why? Only 5% of copper is produced in India. Remaining 95% of copper is coming from Latin American countries, Peru, Chile, all. We get the copper concentrate from them, we happily refine it and do the rest of the things. So this is the situation. Then if you see the Google surf and just put it, how many minerals we produce. Last 15 years it is very standard, 89 minerals we produce. But in that 89 minerals, only 5 minerals are in the sphere. You can take it is our fingertips, iron or limestone, bauxite, all those things only. So you have a special policy for national steel policy. Where, for other minerals, where is the policy? We have not gone into the nitty-gritties of other minerals. We are still simply sitting national steel policy 2015, 2025, now we are going to come up with 2030. So this is a cozy picture which I am presenting, where we have just framed critical minerals, where we don't have any resources on critical minerals, where we are searching in and out of the context. So within these 75 years of independence, what we have done, we have done good mining, no, not at all. All these tailings, now we are working for critical minerals, which we should have done it some 20 years before. I think I should envy and pity on Dr. D. Singh, because he is the only person standing in between us. He is a person supporting for rare earths in the critical minerals sector, because he is operating in a very, very, very tough condition, because he is extraction is 0.06 because it is 1 by 100. Whereas the RE recovery is 60%, he is operating on 0.06. That itself shows how tremendous effort he has put into this domain to at least safeguard us in rare earths in this critical minerals junction. So this is the picture I want to put up. We had some national mineral policy in 2019 where we have not thought about critical minerals. As soon as COVID subsided, we thought of another C term, then we catch hold of critical. Everybody just wake up, every morning you have critical minerals in Jammu, you have critical minerals in Tamil Nadu, all. But nothing is going to come out in another 7 to 8 years. I just bet upon, if anybody can stand up in this audience and tell within 5 years I'm going to come up with the critical mineral mines, no. This is not going to happen. We should blame ourselves actually. I'm not blaming anybody, we should blame the policy makers because we have never thought of the policy on critical minerals. Simply just went up with the wind. Whatever comes, I'll take, because China was giving freely for us as an import. So we are happily dwelling upon all those things, making it, and suddenly one fine day, now our visionary Prime Minister has come up and told that Atmanirbhar. Then we are thinking, even in Atmanirbhar we are not 100% Atmanirbhar. 70% we borrow things from outside and 30% we make until Atmanirbhar. This is the thing which we are making ourselves, we can tell is a big problem. So now I will go into my real business of national critical mineral missions. Just I want to put knowledge food for thought, that's all, because before going to lunch people should think why this critical minerals seminar is happening today. If you take the CRISP, nicely pointed out, CRISP, I should compliment the person who has given this particular wording CRISP, because in CRISP we don't have only C, we have RISP is missing. We don't have recycling, we don't have innovation, separation and then processing. Now these are baby steps which we are taking. Recycling has just one. And I think innovation, it is bits and pieces in CSR institutes or everything we have to stitch upon. Separation, even that remains the same, and then processing. It is all there, but we are not stitching the forces together. There are good brains in our country, but there is lack of synergy between all these good brains. I think now ISM has been credited with the Center of Excellence. They should bridge the gap and do some justice for this particular CRISP to flourish in the new course. So if you see the strategy, why this particular critical minerals is gaining for momentum, we have identified the critical minerals in 2023. I was also a part of that mission in 2023. We identified 30 critical minerals into the kitty. Committee was headed by Ministry of Mines. So these are the strategies where we have to promote research, development, create a stockpile of high critical minerals, because we don't have any high critical minerals, but simply we have coined the term, we have to stockpile it. When we are going to stockpile, I don't know. I am very clear on my path. Focused exploration, that is happening now because of Ministry of Mines, some sort of exploration activities, courtesy Geological Survey of India. We encourage private participation because all these days the government is keeping the doors within themselves. Now they have opened the floodgates to the private sector for the critical mineral exploration program. Create a new legal framework, acquire foreign assets, tax credits, participate in multilateral initiatives on critical minerals and mining, leverage lines of credit given to mineral-rich countries, and then increase recycling rates. The last point has gained momentum in recent years because some 2-3 good companies have come into the sphere and they are doing recycling on a wholesome basis. So these are the major geographies who have identified the critical minerals, and India has identified 30 critical minerals, which now has been narrowed down to 24 based on the requirements of renewable energy, clean technology, and transition to a sustainable low carbon existence. So this is the national critical minerals which was floated on in January 2025. So the focus is on the secure long-term supply chain for critical minerals, mineral exploration, mining beneficiation, processing, recovery from end-of-life products. So these 24 critical minerals comes under Part D of the first schedule of MMDR Act 1957. The mission is implemented for a period of 5 years from 2024 onwards, and it will end by 2031 March. So this is a scheme which was approved on 29 January. So these are the objectives: secure a long-term supply chain and then strengthen India's critical mineral value chains. So the notification was issued on 27 January, and as pointed out, it is for 7 years. So these are the components in the critical mineral mission. So there are some 7 components: enhancing domestic production, foreign asset acquisition, recycling, trade and markets, R&D, skilling and fiscal incentives. So enhancing domestic production, now there are 7 centers of excellence. They should chip into this particular sphere and do some justice. Foreign asset acquisition, talks are going on with Argentina, Australia and some other Latin American countries. Recycling has recently gained momentum. Trade and markets, all those things, it is up to the markets to decide. We don't have any control on critical minerals because China is dictating terms on this. So R&D is happening in CSR institutes. Now at least this critical mineral mission, I think it will stitch on all these aspects. And skilling, where we are lagging is skilling because we don't have any good skilling institutes. Now we have to give due importance to skilling. And then finally comes the fiscal incentives. So this is the mission's financial outlay. It is totally for 34,300 crores. I don't want to go into the details of that. In that actually the PSUs and privates are expected to chip in from around 18,000 crores. So these are the expected outcomes, domestic and foreign sourcing, strengthening value chains in skill development, metal processing parks. So that some other things have happened like Sir, I will share the presentation. So I think this metal processing park, IRL has opened a theme park in Bhopal. So things are happening, but it is not happening in the speed it should happen. That is the main problem in Indian context. So what are the things which has happened in the last 2-3 years is GSA has undertaken 195 exploration projects for critical minerals and 230 projects in this particular current year. And National Mineral Exploration Trust is there is a trust to fund for these exploration projects. They are funded for 62 projects. Critical minerals, 34 blocks have been identified, and the 6th tranche has happened last week for 23 critical mineral blocks. And the first tranche for auction of 13 exploration blocks has also happened. So these are Kabil. There is an entity called Kabil which is doing all sorts of due diligence for this. Kabil is a consortium of MECL, HCL, and NALCO. So they are in talks for 5 lithium brines in Catamarca of Argentina. And we are also discussing with Zambia for 9,000 square kilometers of geological mapping, which is being jointly explored by GSA and MECL. And the Ministry of Mines has recommended an Indian project admin. I think I don't want to throw light on that because everybody knows about it. So the other components, if you ask me, then this is one more scheme which was launched for the recycling. That's why I told you, recycling has gained a little bit of a momentum because government has specially allocated 1,500 crores. It is launched on 3rd September. The scheme is eligible for 6 years tenure. Eligible feedstock will be e-waste, lithium-ion battery, scrap, and other than e-waste, catalytic converters, and end-of-life vehicles. Beneficiaries will be existing large and small recyclers as well as new recyclers. That includes 7 startups also. And the final thing is that my Ministry of Mines has recognized 7 institutes, 4 IITs and 3 IITs. I think under that ISM is also a part of it. So this is just a broad where the upstream, midstream, downstream and circularity is concerned. Actually, midstream is the only thing which is lagging in our sector. So we don't have a concrete midstream in the partners in that where we have to develop the technologies and think some labs like CSR labs and BARC, DMRL are doing good justice on this. So these are the blocks where which particular states are contributing. Rajasthan has given to Madhya Pradesh, Maharashtra, Karnataka, but you can see what that is called CL. CL is composite license. Composite license, it is like from composite you have to come to the mining license. That itself will take 3 to 4 years if you do it in a very dynamic way. So I think that's why I told you initially 7 years is the best bet. I can tell that first critical mineral mine can be opened in India. There are other opportunities like you can work on tailings, other things. So that I think ISM should explore all those opportunities. And this is a mineral-wise auction summary which has happened for starting from graphite, phosphorite, vanadium. So these are the different minerals for which all these auctions have happened. And the momentum across the government sector is that there are the forward actions happening. This is happening for the last 1 or 2 years. I just listed, I don't want to go into the details. Everybody is now chipping into this sphere. And I think with the consolidated efforts, I think another 2-3 years we should do some justice in respect of critical minerals. And this is a high-powered committee which has been formed by the government, where even from Niti Aayog, almost all the ministries are there, and there are 5 nominated experts: CSR, IMFTs, NFTDC, Oil India, Loham. There are recyclers who are doing recycling for cobalt and nickel, and finally it is Alpine also is there. Thank you for the opportunity.
Thank you very much, sir. We'll take 1-2 questions. Please.
Good afternoon, sir. My name is Harshit. It was a very good research presentation that you had. I have one question, sir. When you talk about foreign asset acquisition, are you talking about primary assets or are you talking about secondary sources as well?
No, we are talking about only primary assets.
But why not secondary? What is the problem with secondary? It's asset.
The secondary assets we have in our in-house actually. There are a lot of secondary assets like we have red mud, we have fly ash. We have to ponder upon secondary assets. If you bring, how will you bring it secondary assets? You can just tell me.
There are a lot of scraps which are in tons all over the world which are being imported into India. Example, copper being then motor scraps are there, electronic e-waste are there, which are containing very precious and very heavy rare earth also.
That is happening. That is exclusively for recycling sector to decide whether they want to bring foreign scrap or with Indian scrap we can manage. Now we can manage with Indian scrap also.
But if India does not recognize foreign assets, secondary assets,
we should not be left as a dump yard, because once if you allow the sector to open up, no, they'll use as a dump yard. All the countries will dump on that, where already we are a garbage pile where Swachh Bharat mission is also operating. One more Swachh Bharat mission 3 we have to constitute then. But it will be very difficult.
Can't we just open it to like very particular elements and not to all these scraps, like not for all these scraps? This will help us to like batteries. India has a lot of batteries, but they're not available all the time.
I can tell you, actually I'm operating 2 committees, one for aluminium scrap and one for copper scrap. Actually there is a BAS is one institute, Bureau of Indian Standards. 7 years I am lingering from pillar to post to fix some standards for aluminium and copper. Then you see what will happen for critical minerals. So this is the current status of the government sector itself, because even in government synergy is not so easy. One fellow will pull the socks, 1 year will derail. So I have to go back, go do the course correction, come back. By that time the second person will derail. This is what is happening. 7 years the committee is in a loose-ended committee. We have not done any justice to that also. So it is very easy to speak from that side. Sir, you can bring this scrap, but there are a lot of standards which needs to be fixed, or else people will use India as a dumping yard.
China is importing very heavily. They must have had us.
No, we will have the discussion during lunchtime because. Thank you, sir. Actually, one more question. One more question. Yeah, this is the last question.
Thank you, sir, for a wonderful talk. I just had one simple question. Like, of course, the government is constituting several COEs and all that. How can private universities or state universities, other universities be part of this mission? Other than, say, NRF funds and all that?
Actually, madam, universities, they come up with publishing papers, academia. We don't want that to happen. We want only concrete policies. Just if any university comes and tells that within 2 years we'll do this particular project, where I can bring secondary resources into recycling fold, that sort of projects we are ready to take up actually. Even I think ISM will be ready to bet upon that actually.
Yeah, how can we approach, sir? I mean, I work at Atria where we are trying to do something like this.
So you just ask for the project and then see how viable is the project, cost-wise, technical-wise, everything. So that is how you have to do the due diligence.
Like you are saying through NRF or such schemes.
When funds are available, funds is not a constraint at all, no. But only thing I think we wanted really concrete projects actually, there should be some deliverables. It should not be that they use you as a tool to do some R&D activities, then they'll tell bye-bye and leave the scene. That we don't want to happen. If you want to have, you have to have a flow sheet, master flow sheet where this is the final product which you are going to make and this is the time period. Then the nitty-gritties can be discussed.
Thank you, sir.
Thank you very much. I know there are many questions, but we will not take right now. During lunch time, we will definitely take and we will discuss. A big round of applause for our presenter. I request session chair to give some minutes. Thank you.
Chair and co-chair for their contribution.
May I now request Professor Shravan Kumar to felicitate the chair and co-chair with our momentous.
Dhanbad Singh sir, Dr. C.M. Jayariya, Dhanbad Tiwari, Director of Materials Group, our Computer Center, and Sri Sarma sir from Niti Aayog. And the talks were very enriching. But actually, you could not give more just time, shortage of time, but I think many more questions will be there. So you may ask and discuss, because this is an opportunity you will get, not this type of gathering or expert at one platform. So again, thank you very much for this opportunity for you to chair this session. Thank you.
Ajit Bhaiya.